Hello students, in this e-lecture we will continue the topic probability and discuss about independent events. Let's understand independent events with the help of examples. Students, when a coin is tossed twice, the probability of getting a head on first toss is 1 by 2. The probability of getting a head on second toss is also 1 by 2 regardless of the outcome of first toss. Suppose Indian cricket captain has lost the toss in last 5 matches. What is the probability of his winning the toss in next match? It still remains 1 by 2. Such events are called independent events. Take one more example. Consider the experiment of drawing a card from a deck of 52 playing cards, in which the elementary events are assumed to be equally likely. If E be the event that card drawn is a spade and F be the event that card drawn is an ace, then probability of event E equals to 13 by 52 equals to 1 by 4 and probability of event F equals to 4 by 52 equals to 1 by 13. Also, E and F is the event that the card drawn is ace of spade. As we know, there is only one ace of spade in pack of cards, so probability of E intersection F equals to 1 by 52. Now, probability of E given F equals to probability of E intersection F upon probability of F equals to 1 by 52 upon 1 by 13 equals to 1 by 4. Since probability of E equals to 1 by 4 and probability of E given F is also 1 by 4, so probability of E given F equals to probability of E. So we can say that the occurrence of event F has not affected the probability of occurrence of the event E. Students, we also have probability of F given E equals to probability of F intersection E upon probability of E equals to 1 by 52 upon 1 by 4 equals to 1 by 13, which is equals to probability of event F. Again, probability of F given E equals to probability of F. It shows that occurrence of event E has not affected the probability of occurrence of the event F. So, E and F are two events such that the probability of occurrence of one of them is not affected by occurrence of the other. Such events are called independent events. So, we can say two events E and F are said to be independent if probability of F given E equals to probability of F and probability of E given F equals to probability of E, provided probability of E is not equal to 0 and probability of F is also not equal to 0. Now, by multiplication rule of probability, we have probability of E intersection F equals to probability of E multiply probability of F given E. Marked it number 1. If E and F are independent, then 1 becomes probability of E intersection F equals to probability of E multiply probability of F. Marked it number 2. So, definition is, let E and F be two events associated with the same random experiment, then E and F are said to be independent if probability of event E intersection F equals to probability of event E multiply probability of event F. Also, we can extend it if three events A, B and C are independent, then probability of A intersection B intersection C equals to probability of A multiply probability of B multiply probability of event C. Similarly, we can extend it for any number of independent events. Let's discuss some examples. First is, if probability of event A equals to 3 by 5 and probability of event B equals to 1 by 5, find probability of A intersection B if A and B are independent events. As A and B are independent events given to us, this implies probability of A intersection B equals to probability of A multiply probability of B. Substitute the values. It is equals to 3 by 5 multiply 1 by 5 equals to 3 by 25. Next question. A die marked 1, 2, 3 in red and 4, 5, 6 in green is tossed. Let A be the event, the number is even, and B be the event, the number is red. Are A and B independent? Students, to check that A and B are independent, first we find probability of A, then probability of B, after that probability of A intersection B. If probability of A intersection B equals to probability of A multiply probability of B, it means events are independent. Now, the sample space for dice will be a set with possible outcomes 1, 2, 3, 4, 5 and 6. Let A be the event that the number is even. So, favorable outcomes of A are 2, 4 and 6. This implies probability of A equals to 3 by 6 equals to 1 by 2. Now, let B be the event that number is red. On the dice, 1, 2 and 3 are written with red color. So, favorable outcomes of B are 3. So, probability of event B equals to 3 by 6 equals to 1 by 2. Now, A intersection B means event in which even number in red color. There is only one favorable outcome, that is even number 2. This implies probability of A intersection B equals to 1 by 6. Now, probability of A multiply probability of B equals to 1 by 2 multiply 1 by 2 equals to 1 by 4. So, probability of A intersection B is not equal to probability of A multiply probability of B. Therefore, A and B are not independent events. Let's discuss some more results related to independent events. If E and F are independent events, then first is E and F complement are also independent events. Second, E complement and F are also independent events. Third, E complement and F complement are also independent events. Let's prove the first one. If E and F are independent events, then E and F complement are also independent. Since E and F are independent, we have probability of E intersection F equals to probability of E multiply probability of F. Marked it number 1. Students, probability of E intersection F complement equals to probability of E minus probability of E intersection F. We have learned this result in class 11th. Now, using the equation number 1, we get probability of E intersection F complement equals to PE minus PE multiply PF. Here, PE is common, so this is equals to PE multiply 1 minus PF. Also, 1 minus PF equals to PF complement. So, we get probability of E intersection F complement equals to probability of E multiply probability of F complement. So, we have proved that if E and F are independent events, then E and F complement are also independent. Students, similarly you can prove the remaining two parts yourself. Next, if A and B are two independent events, then probability of A union B equals to 1 minus probability of A complement multiply probability of B complement. Students, we know that probability of A union B equals to probability of A plus probability of B minus probability of A intersection B. As A and B are independent, so probability of A intersection B equals to probability of A multiply probability of B. So probability of A union B equals to PA plus PB minus PA multiply PB. Now PB is common from second and third term. Therefore, probability of A union B equals to PA plus PB multiply with 1 minus PA. Replace 1 minus PA with PA complement. We get probability of A union B equals to PA plus PB multiply with PA complement. In next step, write PA as 1 minus PA complement. Then take PA complement as common from second and third term. We get 1 minus PA complement multiply with 1 minus PB. In next step, write 1 minus PB as PB complement. So, we have proved probability of A union B equals to 1 minus probability of A complement multiply probability of B complement. Students, while solving the question, if required, you can directly apply this result. Also, we can extend it for 3 or more events. Like if A, B and C are independent events, then probability of A union B union C equals to 1 minus probability of A complement multiply probability of B complement multiply probability of C complement. Now, home assignment. Revise all the concepts discussed in this e-lecture and try to solve similar questions of exercise 13.2. Thank you.